this demonstration, we will use the new Autodesk Ember printer as we see how Fusion 360 can be used to improve an engineering team's product development process. The Ember printer was released over the summer. The electronics are shared under a Creative Commons Attribution Share Alike license, the same license under which we've shared Ember's resin and mechanical designs. In layman's terms, this is open source. We have released the engineering files so engineers can customize and tailor the printer to further meet their engineering needs. This printer is relatively small and could fit on a desktop. We have found the need to transport our printer around the office, so in this demonstration we will design a handle to fasten to the top of this printer. Usually, while a product is developed through concept to design to manufacturing, several tools are used to complete the design process. Unfortunately, this usually causes translation issues, and updating a design during a development process does not update from tool to tool. Why wouldn't you expect a greater level of integration from the tools you stake your professional reputation on? Design changes get more complicated and costly the further down in the design process. Fusion 360 is our answer to streamline the product development process, helping design changes propagate to related data that are created throughout the design process. To start, while designing, usually a tool is used to create complex surfacing, then another tool is used to add parametric features, then another tool is used to make direct modeling changes. Fusion 360 is a surface, parametric, freeform, and direct modeler all in one package. We will start by demonstrating this in the Ember assembly. To start off, we will open up a subassembly of the top cabinet assembly. I will open the assembly out of the browser, which is like our assembly tree on the left side. Also notice my feature-based timeline is at the bottom of Fusion 360. We will talk more about these two being in the same environment throughout this demonstration. Now, from within the design, we can see different decisions that were made throughout the design process in the commenting section. For this design, we will use the top-down design approach to design the handle. So let's start a sketch on the front plane. Notice that I didn't have to create a new file or component or activate a component. I just put the sketch at the top level of the assembly. Fusion 360 gives us the ability to have sketches, bodies, and components all in one file. We will start off by using a rectangle and use some construction lines to center this sketch about the hole. Then we can add a few dimensions to fully define our sketch. The advantage of using the top-down design approach is that if the height of the top extrusion changes, the bracket of the handle will always remain 3.5 millimeters above the extrusion and centered over the hole. Now let's turn this 2D sketch into 3D geometry. I will select this top profile. Notice Fusion 360 is intelligently guessing what type of operation I would like to use. In this case, Fusion 360 is joining the new extrude to the top extrusion component as highlighted in the browser. Now, if I wanted to select another profile that causes this extrude to run into an existing body, it will automatically convert into a cut operation. No need to have two different commands for similar Boolean operations. Of course, I have the ability to change to join, cut, intersect, or add a new body or component. In this case, I will create a new body. I could create a component anywhere in the design process, but I will demonstrate this later. Now I have a body that is overlapping over this aluminum extrusion. We can see this interference with an interference detection. To get rid of this interference, we can use a combined Boolean cut operation. This will cut out the interfering section. There's an extra body from this cut operation on the inside which is unneeded. We can choose to remove this body and it will place a feature in the timeline. If I ever need the body back to use in this design, I can simply roll back or suppress the removed feature. Now, I know I want the handle to be above the bracket by 25 millimeters, so I can create a sketch on the face to locate the handle. As I'm sketching, I can type in the dimensions of the sketch entities to sketch and define the sketch at the same time. This will truly speed up my sketching process. Up to this point, we have been parametrically designing this bracket around the top cabinet assembly. Let's go ahead and jump into the freeform environment. We'll start off by using one of the primitives, and then we will use simple push-pull gestures to sculpt our design into our desired shape. We can input our desired length and diameter of our handle. Now, when I drag this slider, we get more or less faces depending on the direction I slide. Ideally, we would like to place more faces in areas of higher complexity. Using T-splines technology, we can add more faces where desired rather than having a lot of faces across the entire body, which will slow down my computational time. Now, I want to add symmetry about the front and back of the handle. Fusion 360 will give us a green line for our symmetric plane. When we start sculpting, we can select faces, edges, and vertices to manipulate. Selecting faces influences our design more than edges and vertices, and then selecting edges influences higher than vertices. Next, I have a reference image I want to use as a guide for our handle assembly. I will insert this as a canvas onto the XY plane. We can resize and relocate the image over our body. In addition, I will change the opacity and allow the image to be visible through the body. When importing images, there's no physical size associated with the image, so we can use the calibrate tool to size the image to the body we created. Next, I will start forming our body to the image. Unfortunately, moving this edge does not give me the desired result. In this case, we need to add some edges to be able to get the desired result. I will select this inside edge and insert two edges on both sides. Now I can use these newly created edges to manipulate our design. Adding these new edges created a T-junction. This is where the T in T-splines comes from. We can add complexity by adding edges, and it forms these T-junctions. Once I have the entity selected, I can use the triad to either translate, scale, or rotate the selected entity. We can select this entire edge and make a flat portion for the palm of my hand to rest on. I am designing half of the handle, and I'm going to mirror about this middle plane in the future, but I am worried about causing a sharp point in the middle. So we can mirror the T-spline body, and notice that this body is always trying to retain its curvature continuous nature as I make changes. Now we've come to a point where we want to see some different design ideas. I can copy and paste my body and move it above my current body. Here we can make some changes to the newly copied body to quickly iterate on many design ideas. This will help flush out some bad ideas before arriving at the perfect idea for our concept. We will use the soft modification to influence the fall off as we manipulate these faces and edges. I like the new design, but I think the original handle will be more versatile, so we will run with the flat handle design. Next, I want to start working on the transition to the bracket of the handle I created earlier. I'm going to use this great tool called Convert. In this case, Convert can be used to convert parametric face into a T-spline body. Then I could start deleting these faces where I want the transition to occur. This new body is just like any other T-spline body. I could use my push-pull gestures to scale and move. I can also add faces where needed to help control the transition. Now I'm set for combining my two T-spline bodies. Let's use a bridge to bridge the gap. Fusion 360 will automatically calculate the transition for our design. This new body behaves just like before, where I can use my push-pull gestures to dial in the shape of our design. Now, I'm just about the point where I've completed the sculpted body, so let's go ahead and finish this form. Once I exit this freeform workspace, the body is automatically converted into a NURBS surface. I can use this just like any other surface in Fusion 360. In this case, I want to use it to form half of my handle. So I will create a boundary fill. This tool will find different volumes from my selected tools. Once I select my tools, I can select the different volumes I want to keep. Then I am left with a few tool bodies and half of my handle. I will proceed with removing a few bodies to keep my browser clean. Now let's work on completing this handle. I sometimes forget where commands are located though, so we can search for commands and add them to my toolbox if I'm going to use them frequently. Fusion 360 makes it easy to locate commands so you could keep your mind on the design. In this case, we searched for the mirror command and then created the mirrored half of our handle. Then we can quickly combine them back into one body. Till this point, we have been working on a body at the top level of this top cabinet assembly. Two main reasons to turn a body into a component is for bill of materials or assembly motion. Fusion 360 allows an engineer to turn bodies into components when convenient in the design process. We can give this new component a part name. Next, I want to create an overmolding for a rubber gripping surface. So let's create a sketch to use as a cutting tool. I will sketch a spline to get a curved gripping surface. In addition, I will create a center line to use for symmetry. If I'm going to apply the same constraint to several sketch entities, I can select the constraint out of the sketch palette and the constraint will remain on, so I can rapidly apply this constraint to multiple sketch entities. No need to control select multiple entities, then select the constraint out of a submenu over and over. Now that our cutting tool is complete, we can split the body in order to create the overmolding. In other tools, I would have to copy the surface, thicken the surface, then combine it back into the original body. Instead, I'm going to use my command for all commands, press pull. When I select faces, press pull will turn into offset faces, which will allow me to place my desired 1.5mm offset. That was too easy to offset that complex surface. Now, when I select an edge, press pull will turn into a fillet. This tool will change depending on what is selected and help design faster rather than searching for the correct command. Now make sure you pay attention. Here's the cool part. I have created a freeform gripping surface for the handle. Then I made some parametric changes to it. Usually when a design change is required to the freeform surface created early in the design process, multiple changes are required between multiple tools. In Fusion 360's integrated tool set, when I make a design change to the surface, the downstream features will update accordingly. No need to recreate surfaces or fix a bunch of red and yellow features in the feature manager tree. Now, this component is floating in space right now and doesn't know how it interacts with the rest of the assembly. Fusion 360 has rethought how designs are assembled. First, the assembly tree and the feature tree are in the same file. Second, this handle was designed in context of the assembly, so why do we need to pull it apart to apply mates or constraints to assemble it back together? We have an as-built joint for components designed in context. Third, when mating or applying constraints, usually an engineer is trying to lock down all 6 degrees of freedom, 3 translations and 3 rotations. This usually takes about 2 to 3 constraints or mates to get the desired motion. In Fusion 360, we apply one joint. We lock all 6 degrees of freedom down and change the joint type to get the desired assembly motion. This will help designs get assembled faster and behave more robustly when design changes are made. Finally, I will go ahead and add a few appearances to our handle. I will access our customizable appearance library to apply a red plastic appearance to the handle and a rubber appearance to the gripping portion. Now that we have completed our design for our handle, we can leave a comment documenting the design changes. This comment will travel with the design and produce a trail of how and when design decisions were made in the design process. In addition, this will save a new version of the design. Don't worry, if I screw up, we can always roll back to a previous version. Let's switch over to the top level assembly. Whoa, you might notice my handle is not in the assembly. Why hasn't it updated? Well, in Fusion 360, we don't automatically update the reference to the latest version. In other tools, sometimes bad design changes are made, and they are propagated to the top level assembly. We allow the user to choose when to update to the current version. In addition, we can always choose an older version, just in case the changes I made would cause errors. This will prevent design teams from having to fix red assembly trees from unwanted changes to the top level assembly. Versioning is inherently built into Fusion 360 and doesn't require a complex PDM system to implement. Now we have a need to produce a rendering of this design for marketing. Let's switch over to the rendering workspace. Here we can change the scene and scene settings, such as adding depth of field to this image. Finally, I could turn on the ray tracing to leverage my computer's hardware to calculate the light bounces in this image. Unfortunately, I need to start producing cam toolpaths to run my Haas mill. While this image is being rendered, it is using up a majority of my computer's resources. Instead, I could start a cloud render. This will leverage the nearly infinite resources of cloud computing. I can set a few parameters, and in a few minutes, Fusion 360 will return a render without having to stall my design team from leveraging their computer's hardware. While that is being rendered, let's check out the design in A360. This is Fusion 360's data management and collaboration tool. A360 is an essential part for a design team to work together and understand how different design data is related. Let's jump to one of the subassemblies of this top-level assembly. In a web browser, I can see what design my file is referencing, where it is being referenced, and any drawings that may have been created. It is also a great tool for non-CAD personnel to collaborate throughout the design process. A360 also displays the related data created during the design process in other workspaces, such as CAM, animations, rendering, and simulation results. Right in a web browser, we can jump into the immersive experience and see the animation created within Fusion 360. In addition, I could jump into the design and interrogate the assembly tree and see which component this design uses, such as what type of fasteners I chose to use for the printing bed. Let's open up the commenting pane. Here we can see different comments that have been made throughout the design process. Usually these are key design decisions made between multiple stakeholders' email boxes. Now I have a centralized location for all design decisions made throughout the design process that can be audited for when and why decisions were made. We could start redlining our design right in a web browser to better illustrate required design changes. Gone are the days where we would have to try to describe with text what we wanted changed in the design. In addition to redlining, we can create comments on points or objects. These will produce a balloon referencing the selected entity to better illustrate what needs to be changed. Of course, any of these comments can be seen in Fusion 360 as well. No matter where you are, an engineer can hop on a web browser and still collaborate on key decisions that need to be made throughout the design process. Now we need some input on a design change from some external stakeholders. From Fusion 360, I could start a live review session. This will generate a link which I can copy and paste into an email. Once my external stakeholder receives the email, they can click on the link and it will open up in a web browser. An interactive web experience will be open in the web browser where they can collaborate on design changes. Here I can choose the driver and make design changes. In real time, the design changes are propagated to their session. In addition, I can choose to make them the presenter. They can collaborate on what needs to be changed from a web browser anywhere in the world. This will truly change the way design teams collaborate with both internal and external stakeholders. Now, I need to send a file to a machine shop for them to start some post-processing work. I can start by sharing a link. Here I can give them access to download the file or password protect the link. Once they click on the link, they will see the design in a web browser. Here, they can choose which file format works best for their post-processing tools. There is no need to download a view or worry about file compatibility or send them the wrong file type. This shared link changes the way design teams will work with external stakeholders. Of course, I can close the link to stop access to the file in case I no longer want to share my design with external stakeholders. Throughout this demonstration, we have seen how we can have multiple designers, engineers, managers, and external stakeholders collaborate on a design. We have also seen how Fusion 360 integrates different modeling techniques, such as freeform, parametric, surface, and direct modeling, all in one package. Now, we will demonstrate how Fusion 360 integrates post-processes such as simulation, CAM, rendering, and animations. These post-processes will update accordingly from design changes made throughout the design process, which will reduce the amount of rework required to set up these processes. We will open up a linear drive subassembly to start setting up the required procedures to start generating G-code to start running my Haas mill. CAM toolpaths can be generated in the CAM workspace, which will update from design changes. Once in the CAM workspace, we can see different CAM commands to help program our part. We can start by creating our first setup. We will orient the Z-axis and pick the location for the pickup of our part. We will use this corner to probe when locating our part in our machine. Normally, we would take this time to measure our stock with calipers, and we can input these values on the stock tab to ensure our part is cut to the correct dimensions. Next, we can start by facing our stock to our part. To do this, we can select the facing operation, select the face mail, and hit OK. In a few clicks, we have generated our first toolpath. Now, let's start roughing out the inside slot with an adaptive clearing toolpath. Adaptive clearing is a roughing strategy available for clearing large quantities of material effectively. It is unique in that it guarantees a maximum tool load at all stages of the machining cycle. Our roughing toolpath will ensure that wear is uniform across the length of the tool. Finally, let's ensure that we don't crash our tool by simulating our toolpaths. Simulating our toolpath ensures that our parts are being cut correctly and we don't make any costly mistakes such as running the part into a vise. We can use a timeline at the bottom to jump to different points in the simulation to interrogate how our machine will be cutting our part. Finally, we can post our G-code. Fusion 360 has different post processors to run the most versatile of machine shops. Once the G-code is posted, we can look at our code in brackets and make any required changes to the G-code. While I was generating the toolpaths necessary to run my Haas mill, I've been asked to run a finite element simulation to ensure our design can meet a 50-pound load while the printer is in operation. Just like the CAM workspace, we can switch over to the simulation workspace to start setting up our finite element analysis. First, let's start by creating a new study. Fusion 360 has the ability to run static, frequency, thermal, and thermal stress studies. We start by simplifying this problem by suppressing components that are not required for the simulation. Next, we can access our customizable material library to assign an aluminum material to the back plate. One of the most common mistakes while setting up a finite element analysis is either over or under constraining your problem. Fusion 360 allows us to turn on our degree of freedom plot to help solve this problem. This will help visualize what components are still left to be locked down. We can start by adding a few constraints. These holes are fixed to the Ember printing bed, so we can assume they will be fixed. Next, these slots are able to slide along a rail, so we will assume a frictionless constraint. Now we need to add some contacts. Contacts are used to describe how components interact with each other. In this case, I'm going to use automatic contacts. I have told Fusion 360 to look for faces within a 0.1 mm tolerance and make a bonded contact. Fusion 360 will find the corresponding faces. If I need to switch a few to a sliding contact or turn them off, I have the ability to quickly do so. Lastly, I need to add a manual contact. Usually this requires a lot of hiding and showing of components. In Fusion 360, we select the two components, then it will make one of the components transparent, allowing me to select the solid component's face without any trouble. Then repeat the process for the second component. This will speed up the process to set up any finite element analysis problem. Now we want this assembly to survive a 50-pound load experienced while the printer is in operation and have a factor of safety above 3. So let's apply a 50-pound load and change the direction that the load is being applied. The last thing to do before solving is changing the mesh. Here we can make a finer mesh and turn on second-order tetrahedral elements because we are solving for stresses in this scenario. So let's solve and let Fusion 360 analyze this design. Normally, we would want to ensure that our simulation converges on a stress value. In that case, I would turn on our mesh adaptation tools, which will refine our mesh in areas of high concentration. Now that Fusion 360 has solved our simulation, we can interrogate our results by looking at different plots such as safety factor, stress, and displacement. In addition, we can use tools such as surface probes, slicing planes, and animations to see how stress is distributed through the design as the 50-pound load is being applied. Unfortunately, the current design did not meet our design requirements for a factor of safety of 3. So let's jump back into the modeling workspace to make a few design changes. We can use Fusion 360's direct modeling tools to thicken the inside slot by 0.5 mm. Now, if I was using tools that weren't integrated and didn't reflect the design changes made throughout the design process, I would have to reproduce the work required to set up the simulation and CAM toolpaths. In Fusion 360's integrated workspaces, I could jump right back into the simulation environment and hit Solve again. This integration is required in today's design process to test many different scenarios. Imagine if I had to set up every simulation for a few design changes. In Fusion 360, I can make a design change, jump back into the simulation workspace, and run it again to ensure we have the best design before going to production. Just like the simulation workspace, the CAM workspace will update with a thicker plate. I can right-click on the Setup folder and select Generate Toolpaths to reflect the thicker plate. Then I could run the simulation to ensure my part will be cut correctly. And of course, I could post this out again to send to my machine to start cutting parts with the new design changes. Throughout this demonstration, we have shown how Fusion 360 has integrated different modeling techniques such as surfacing, freeform, parametric, and direct modeling. Also, Fusion 360 integrates different post processes such as renderings, animations, simulations, and CAM toolpaths. These different types of integrations ensure that if a design change is made anywhere in the design process, downstream data also reflects these changes. This will ensure that design teams will save time instead of doing rework. Also, we have leveraged the cloud to collaborate with our design team. We were able to create comments and red lines which illustrate key design decisions. These comments travel with the file and produce an auditable trail of when and why decisions were made. Also, we were able to stay connected to our data via a browser or the Fusion 360 mobile app, which is available for iOS or Android. Finally, we have given access to a variety of tools such as high-end design, visualization, documentation, simulation, and manufacturing tools. Usually these are different tools which each have an expensive price point and subscription cost. Now, Fusion 360 is constantly being updated. Make sure to check out our roadmap to see what we will be bringing into the tool next, or go visit our idea station to contribute different ideas that could be implemented into Fusion 360.